Welcome back to Introduction to Higher Mathematics. In our last lecture, we started to build relationships between sets. We defined the Cartesian product, which combines two sets together to form ordered pairs, which are a specific example of a structure called a tuple. We talked about the arity of an operator. For example, some operators are unary, others binary or ternary, and so on, and use this to extend the Cartesian product to any number of sets. Given two sets A and B, we established relations, which are subsets of A times B, to show how various elements of the two sets are related to each other. We saw how to represent a relation using graphs, or specifically digraphs. We then focused on relations on a single set, of which we were particularly interested in two types: equivalence relations, which show some sort of equivalence between elements and must be reflexive, symmetric, and transitive, and order relations, which establish some sort of hierarchy on the elements, and must be reflexive, transitive, and anti-symmetric. We started with partial orders, then worked our way up to total orders, which let any two elements of a set be compared in some way. And finally, strict total orders, which require that either x is related to y is related to x, or x and y are equal. So let's continue our discussion of relations. This time, rather than focusing on properties of relations over a single set, we're going to look at relations between any two sets, same or different. We're going to look at two particular properties of relations: uniqueness and totality. We'll often be referring to the domain as the left set and the codomain as the right set. First of all, take a look at this relation. Notice that each element in the left set maps to at most one element in the right set, if it maps to anything on the right at all, that is. We say that such a relation is right unique. Think of it this way. If we started with an element on the left and moved along the arrow to the right, we could only possibly end up at one element on the right. We always know where it's going. So mathematically, the way we represent this is that if an element x on the left maps to two different elements on the right, y1 and y2, then y1 and y2 must actually be the same element. Important to note, however, is that in a right unique relation, some elements in the left set may not map to anything on the right set. The stipulation is that they must map to at most one element on the right. Next, look at this relation. In this case, the reverse situation is true. Each element on the right is mapped to by at most one element from the left. This relation, as you may have guessed, is referred to as left unique. So, if we started with an element on the right and moved backwards along the arrow to the left, we could only possibly end up at one element from the left. We always know where it came from. So, if two elements x1 and x2 on the left map to the same element y on the right, then x1 and x2 must actually be the same element after all. Again, keep in mind that not everything on the right may be mapped to. We only require that an element on the right is mapped to by at most one element on the left. That takes care of uniqueness properties of a relation. Now let's look at totality properties. These are a bit easier to notice. Look at this relation. What we notice here is that every element on the left maps to something on the right. No element in the left set is, well, left out. We refer to this relation as left total. Specifically, we would say that if a function is left total, then for all little x in x, there exists a little y in y such that little x maps to little y. Similarly, look at this next relation. In this relation, every element on the right is mapped to by something on the left. No element in the right set is unmapped to. As you might expect, this relation is referred to as right total. So, for all little y in y, there exists a little x in x such that little x maps to little y. Be careful, by the way. The concepts of left total and right total for a relation between two sets are different than the concept of total for a relation over a single set. Make sure you understand this difference. These four properties, left uniqueness, right uniqueness, left totality, and right totality provide a rather convenient basis we can use to define another omnipresent concept in mathematics, the concept of a function. A function is defined as a relation that is both left total and right unique. In other words, for a relation to be classified as a function, every element of the domain must map to exactly one element of the codomain. So, here's an example of a function. In grade school, students are often taught to think of functions as machines. If we think of a function as a machine, every input produces an output, and we always know, unambiguously, what output we'll get. A machine wouldn't be very good if some inputs produce no output. That's why a function has to be left total. And a machine would be equally useless if the same input produced different outputs when you ran it again. That's why a function has to be right unique. When we notate a function, there are two parts we must be sure to write. I personally like to borrow some terminology from computer science and call them the prototype and the definition. In the prototype of a function, we give the name of the function, which we might call f, and then specify the domain and the codomain of the function. We write an arrow between these two sets. You've seen these arrows used for conditionals, and in a way, the concept transfers over. Since a function is left total and right unique, you can always be sure that if you choose a particular element of the domain, then it will always be taken to the same element of the codomain. In the definition of a function, we give a rule that tells us how to map each element of the domain to its corresponding element of the codomain. There are a few possible ways to do this. First of all, we could give a set of ordered pairs, just like we did in our previous lecture with our various relations. This becomes cumbersome or downright impossible for anything but a small domain. So our second option is to let X be an arbitrary member of our domain and show how to find its corresponding member of the codomain. We can place a modified arrow with a vertical bar between them, which is usually read as maps to. So for example, this function definition might be read as x maps to x squared. By this definition, 1 would map to 1 squared, which would of course be 1. 8 would map to 8 squared, which would be 64, and so on. An even more common way to write this, and the most useful way if you have more than one function, is to write the name of the function f with its argument, say x, in parentheses next to it. We would read this as f of x. Then we'd of course give our rule right after, so we might say f of x equals x squared. By the way, does this look or sound familiar? It's just like how we would read predicates. In fact, in a way, predicates can be thought of as functions, where the domain is something from a given set, and the codomain is the set false, true, which is often called a Boolean domain, even though in our case it's actually the codomain of our functions. We often notate a Boolean domain with a double-struck capital B. As we saw earlier, functions are most often first seen written with a lowercase f. Of course, we can name functions just about anything we want. Lowercase letters like G, H, and J are often used too, as well as entire names, or sometimes Greek letters, both lowercase and uppercase. In reality, there's no true restriction on what you can name a function. Try to use some common sense, though. Speaking of arguments, so far, the functions we've looked at have had only one argument. But there's nothing stopping us from defining a function where the domain, rather than being a single set, is actually a Cartesian product of sets. In that case, the input of the function is a tuple rather than a single number. In most cases, we drop the extra set of parentheses and just treat the function like it has multiple arguments. So, for example, I might have the function from z times z to z that takes in two integers and adds them up. We might write such a function as f of x comma y equals x plus y. Similarly, we might have a function for which the codomain is a Cartesian product as well. I might define a function from r to r squared that takes in a number, perhaps an angle, and gives me an ordered pair containing the x and y positions on the unit circle corresponding to that angle. In other words, the function f of t equals cosine t sine t. If you studied parametric equations, this representation should look familiar. In fact, there's no reason we can't combine the two. We could, if we so choose, make a function of 3 variables that spits out an ordered 4-tuple. Our definition of a function is rather flexible and accommodates these possibilities just fine. Let's rewind a moment. Suppose our function f maps x to y. In other words, f of x equals y. Then, to introduce a key word here, we say that y is the image of x, or more specifically, the image of x under f. I'm not sure exactly why this terminology came to be the case, but I like to think that it comes from lenses in physics. When you look through a lens, you see the image of objects on the other side of it via refraction. Each individual part of the object in the real world has a particular place it corresponds to on the image inside the lens. If you'll pardon the horrible pun, keep this image in the back of your head as we continue from here. Now, suppose we have a subset A of our domain. Every element of A has its own image in the codomain. So we can extend our idea of the image a bit and say that the image of A is the set made up of all the images of A's individual elements. So, looking at our earlier example of a function, if A is the set 1, 2, 3, then the image of A is the set A, B, since 1 maps to A, and both 2 and 3 map to B. We can reuse our function notation, or, as we might say in computer science, overload it, and say that f of A is that set AB. In set builder notation, we can say that f of A is the set of all little y in y for which there exists an x in A such that f of x equals little y. We can extend our concept of the image just a hair further. If we can talk about the image of a subset of our domain, since any set is a subset of itself, it's inevitable that we talk about the image of the entire domain. As you'd expect, right from the previous definition, the image of our entire set X under F is the set of all elements of Y that are mapped to by some element of X. Or, again using set builder notation, f of x is the set of all little y in y for which there exists a little x in x such that f of little x equals little y. We have a special name for this set. We call the image of the domain of a function the range of that function. So in this function, the range is the set A, B, D, E. Note that the codomain and the range are not the same thing. Rather, the range is a subset of the codomain. There may be elements of the codomain that are not mapped to by any element of the domain. Or there may not be. That's something we'll talk about in a moment. We can also turn the idea of the image on its head a bit. Suppose we look at a particular element of the codomain. Let's say A. We might want to know what element or elements map to A. In our case, we can see that 1 maps to A. So we can call 1 the preimage of A. Now look at B. 2 different elements can map to B, 2 and 3. So the preimage of B is actually a set of 2 values this time, 2, 3. So we can define the preimage of an element of the codomain as the set of all elements of the domain that map to it. In particular, the preimage of little y is the set of all little x in X, such that f of little x is little y. The common notation for this is to write our f with a -1 superscript, as if it's the -1 power of f, and read it as f inverse of y. Don't worry too much yet about why we treat it like an exponent. The reasons become clear in time, I promise. Just think of the -1 as meaning in reverse. And of course, we can extend the concept of preimage much in the same ways we extend the concept of the image, and talk about the preimage of a subset of the codomain. For instance, the preimage of the set A, B would be the set 1, 2, 3. Now, suppose you were to take a graph of a relation and reverse it. The domain now becomes the codomain is your new domain, and the arrows change to reflect this. What you would have is what's called the inverse of that relation. More specifically, given a relation R, which is a subset of x times y, the inverse of R, notated as r to the -1 and read as R inverse, will be a subset of y times x instead, containing all the ordered pairs that were in R, but in reverse order. So the inverse of a relation gives us a way to talk about the preimages we just discussed. Note, by the way, that the first relation we gave is a function, whereas the second relation, its inverse, is not a function. So the inverse of a function might not be a function itself. Well then, what does it take to ensure that the inverse of a function will itself be a function? To answer that, we'll need to talk about some special types of functions. Remember that we said for a relation to be a function, it must be left total and right unique. But functions become even nicer to work with as we add other properties to them, and thus the special types of functions we're about to talk about are seen everywhere in mathematics. Let's see what each one does. First of all, we could start with a function and then add the property that it's left unique. For instance, we might have this function. Now we've got a function that's both left unique and right unique. So every input pairs with one output, and no two inputs have the same output. We call such a function injective, or more colloquially, we call it one-to-one. We can also say that f is an injection from x to y. Second of all, we could start with a function and instead add the property that it's right total. For instance, we might have this function. Since our function is also right total, we're guaranteed that every element of y will be mapped to by something in x. We would call this function surjective, or to use a less fancy term that's not from French, it would be called onto. As before, we can also say that f is a surjection from x to y. Another way to phrase this is to say that a function is surjective if its range is its entire codomain. Now, injective functions and surjective functions are nice to have, but we can do even better. Suppose we start off with a function, and then we also make it both left unique and right total. So for example, our function might look like this. Notice that this function has all four properties. It's both left unique and right unique, and it's both left total and right total. We would call this function bijective, or say that it's a bijection. So a bijective function is one that is both injective and surjective. Bijective functions are special for two particular reasons. First of all, if we can find a bijective function between two sets, then that means that both sets have the same number of elements in them. We would say that they have the same cardinality. We'll talk more about cardinality later. For a more intuitive example of a bijection, consider the following scenario. A teacher in elementary school tells her students to get seated, and each child sits down in his or her seat. Now the teacher knows she has 25 students and 25 desks. So while she could count all 25 students, she might instead use the idea of a bijection to make sure at a glance that each student is seated correctly. Of course, the teacher doesn't think to herself, "Oh, I've got a bijection," but you get the idea. How could she do this? Well, she would need to check 4 criteria. First, every student should be in a seat. No student should be standing. This means that the relation between students and seats is left total. Second, no student should be sprawled across multiple seats. This means the relation is right unique. So now we know the relation is at least a function. Third, no seat should have more than one student sitting in it. This means the function is left unique and is thus injective. Finally, every seat should have a student in it. No seat should be empty. This means the function is right total and is thus surjective. If all 4 of these properties are true, then all students are seated correctly, and the function from students to seats is in fact a bijection. The second reason that bijections are so useful is that if a function is bijective, then its inverse is guaranteed to also be a function. For this reason, we say bijective functions are invertible. Why is this? Why does a function need to be both injective and surjective for its inverse to be a function? Well, let's take a look. Consider the function we ran across earlier and its inverse relation. Why isn't the inverse a function? Well, first of all, the inverse is not left total. This is because the original was not right total. So if a function isn't surjective, when we look at its inverse, not all elements in the domain of the inverse will be used. Second of all, the inverse is not right unique. This is because the original was not left unique. So if a function isn't injective, when we look at its inverse, some elements in the domain of the inverse might map to multiple elements in its codomain. But why do we care so much about whether the inverse is a function or not? Remember that with a function, when we specify an input, we know exactly what the output will be. But if a function is also invertible, then if you give me the output, I can tell you exactly what the input was in the first place. This is essential in mathematics because it lets us reverse our processes, especially when we're doing algebra. When we talk about abstract algebra and groups, you'll see just how important inverses are. Right now, the most important thing is to know that you can use them to reverse the effects of a function. So having talked about the properties of a single function, it's time to do just like we did with propositions and sets and, what else? Chain them together. When we chain functions together, we do so using something called composition. Think again about the idea of a function as a machine. If we were to link multiple machines together, then the output of the first machine might be the input of the second machine. So, suppose I have two functions. Let's say that f takes in elements in x and spits out elements in y, and then g takes in elements in y and spits out elements in z. Well, we could then plug an element of x into f, take the result and plug that into g, the result of which would be an element of z. In other words, we've managed to create one big machine that's basically a function from x to z. Now, pay special attention to how we notate this. If I have a little x that I plug into f, the result would be f of little x. Then if I took that result and plugged it into g, I'd have g of f of little x, written like this. The parentheses tell us that the result of f of little x has become the entire input for g. So, if I want to write down the composition of f and g in this manner, I would write g first, then a little circle, and then f, which I would read as g of f, which is a function from x to z. Note that you plug a number into f first, even though it comes second when we write it. But just think about how we'd write it if we were using nothing but parentheses, and it makes perfect sense why we write a composition of functions in this order. Now, with compositions in mind, let's look at a very important composition. What happens when we compose a function with its own inverse? In other words, what is f inverse of f of x? How about f of f inverse of x? Take a look again at this bijective function. Let's find out what f inverse of f of 4 is. Well, f of 4 is e. Then, plugging that into f inverse, we can see that f inverse of e is 4. Well, look, we got the exact same thing back. Now let's try the other one, f of f inverse. Let's say that we start off with c. Then, f inverse of c is 5. Then, plugging that into f, we find that f of 5 is c. Again, we get the exact same thing back. This is no coincidence. In fact, it makes perfect sense. We said that f inverse has the effect of undoing f, as long as f is a bijection. So, if we compose a function with its own inverse function, in either order, then when we plug a number into this composition of functions, we'll always get the same thing out. If we were to make this composition into a single function, we would call it the identity function, the function for which the output is always the same as the input. One last thing I'd like to go over with functions. Sometimes a function doesn't quite have the properties we'd like. Perhaps it's not injective, or maybe it's not surjective. It might not even be a function at all because it's missing some vital properties. But with some clever manipulations, restricting the domain or the codomain, we can mold our function into just what we're looking for. First, let's look at how to ensure totality properties of a function. Consider this relation. This relation isn't a function yet because it's not left total. We actually would call this a partial function. However, we can turn it into a function by restricting our domain to only the set 1, 2, 3, 4. By eliminating 5 from the domain, we ensure that no element in the domain is left out of our relation. Now, we indeed have a function. If we make a similar change to the codomain and eliminate D and E, our function becomes surjective. So we can make sure that a relation is left total or right total by eliminating elements that are disconnected from anything. Now let's talk about how to ensure uniqueness properties of a function. Consider this relation. Again, this relation is not yet a function because it's not right unique, though it is something called a multifunction or a set-valued function. If we want to turn a multifunction into just a function, we can do so by eliminating elements of the codomain. So, if we were to eliminate b from the codomain, our element 1 in the domain is only left mapping to 1, and our relation is once again a function. It's not injective, though, since both 2 and 3 map to C, and both 4 and 5 map to D. But, as you may expect, we can fix this as well by eliminating 3 and 4 from our domain, making our function injective. So again, by creatively restricting our domain and codomain, we can make sure a relation is left unique or right unique. By the way, multifunctions do have all sorts of uses in mathematics. For example, consider the function f of x equals x squared from r to r. Note that this function is not injective. For instance, f of 3 equals 9, but f of negative 3 equals 9 as well. This means that f inverse of x is not a function, but instead a multifunction. Every number except 0 actually has 2 square roots. The square roots of 9 are 3 and negative 3. So of course we can create a square root function by eliminating some of these roots. We could choose whichever ones we want to eliminate, but in practice we usually keep around the ones that are most convenient to use. So, since every non-zero number has a positive square root and a negative square root, we usually get rid of the ones with the pesky negative signs and define the square root function to always give the positive square root of the number, or of course 0. We call this the principal value of the square root relation, the simplest and most convenient value of the multifunction. So by restricting our domain to only the principal values, the inverse goes from being a multifunction to being at least a partial function. By restricting the codomain as well, we can ensure that our function is bijective, and its inverse is a full-fledged function as well. That's it for functions. I know that was a lot of material to take in, but functions will be addressed in many of the lectures to follow. Next time, we'll be looking at one of the oldest fields of mathematics and history, number theory. See you next time.